Thanks everyone for coming. I'm John Pavan, and I'm currently a team lead at Bloomberg. And today we're going to be talking about testability and API design. Unfortunately, when we were writing this talk, we did not realize the level of interactivity at this conference. And while you are certainly welcome to interrupt and ask us questions at any time, we have put numbers on it. So if you'd like to hold your questions until the end, you can refer back to specific slides pretty easily. That said, I'd now like to turn over the microphone to Aram to start off the presentation.
Thank you, John. Audio good? Okay. Hello, I'm Aram, or Aram. Either is fine, Aram. I'm a software engineer at Bloomberg, and outside of Bloomberg, aspiring cartoonist. So talk to me about that. First things first, as it happens, we are going in alphabetical order. So I will cover the first two parts, then John, and then Lukas. So let's go over some background and basics. Let's establish some terminology for the talk, so we start off on the same page. So you all are already at this talk, so we're probably preaching to the choir here, but allow us to state testing is important. Testing can verify both the happy path and unhappy path behaviors of your code. Happy path behaviors, of course, meaning how your component behaves for the intended use case when everything goes as expected. And unhappy path, of course, meaning how your component behaves under unexpected conditions, such as I/O failures and whatnot. Automated tests can be set up to run regularly. They protect against regressions and add value over time. This is, of course, in contrast to manual tests, which don't add value over time. They tend to add cost over time. So we definitely want users of our library to be able to set up automated tests easily. And of course, unit tests, integration tests, and system tests have different roles and provide different benefits, as we shall also cover shortly. Okay, so no talk on testability would be complete without the pyramid. So here we are. As we go up the pyramid, we have more isolation and less granularity. As we go down the pyramid, we have more isolation and more granularity. So at the top of the pyramid, system tests, they tend to be slow. They can take up to maybe days. Integration tests are faster, minutes, maybe hours. Unit tests at the bottom, they may take milliseconds to minutes. So we want fewer system tests and many more unit tests so that our tests run in a reasonable amount of time and are easy to maintain. Let's very quickly look at each in turn. So, unit tests. Let's test code in isolation. I'm going to very quickly go over these. Unit test tests a component in isolation with external dependencies stubbed out. A unit test verifies both happy path and unhappy path behaviors. A unit test verifies that the component or class does what is expected. In a unit test, other components and classes need to be mocked out. We just want to emphasize once more that a unit test can test unhappy path behaviors. Integration tests. So we've developed bits of code in isolation. Now we want to see if they actually integrate well with each other. So again, an integration test tests a component that is running in the expected environment. This could be the full executable running in a contrived environment. An integration test verifies happy path behaviors, but it can be very difficult to test unhappy path behaviors. An integration test verifies that the component behaves as expected for its expected use case. In an integration test, other executables or system-level dependencies are often mocked out. Okay, system tests, end-to-end testing. Okay. A system test tests an executable deployed to a test environment. A system test verifies happy path behaviors. A system test verifies functionality when integrated into a production system, like system. In a system test, dependencies are not mapped out. In this talk, which is about designing APIs for testability, we'll focus on integration tests and unit tests. So the motivation for us is to design APIs for testability and to design APIs for usage in test drivers. Designing for testability. The question is, how do I, the implementer, test my code? And as we shall go into more detail soon, there is a deep synergy between testability and solid design principles. Designing for usage in test drivers, the question is, how do the users of my library test their code? The API must be usable in test drivers and in integration tests. And if mocking is their chosen approach, I, as the library implementer, must provide mock objects. And as promised, these are the solid design principles that you all know and love. Let's now take a look at them from a testability perspective. So the S in solid. Single responsibility principle. Each class should do only one thing. We can see how writing tests for a class that does only one thing would be easier than writing tests for a class that does a million unrelated things. But we also want to note that adhering to this principle, as well as the interface segregation principle, also means we should separate the public API from the test-specific functions or methods. Sorry, altitude. Open-close principle. Software entities should be open for extension, but closed for modification. We should be able to add new functionality without changing existing code. And here we're especially interested in the polymorphic version of this principle, which involves an abstract interface with multiple implementations. So to add functionality, we don't need to change the interface or existing implementations. We only need to add another implementation of the abstract interface. Also, there's no need to edit existing tests. We only need to add tests for the new extension. And in this talk, we also want to note that sticking to this principle also makes it easy to create a mock for an implementation, since we just need to create another sibling extension that is a mock. Of course, for that to work, the Liskov substitution principle needs to hold, aka strong behavioral subtyping. We should be able to replace a class with any class derived from it without breaking what's using it. So we're able to very easily switch out an implementation with a mock. Moving on. The interface segregation principle states that no code should be forced to depend on methods that it does not use. As mentioned previously, adhering to this principle means that we should keep the public API small. And lastly, the dependency inversion principle. High-level modules should not import anything from low-level modules. Both should depend on abstractions, interfaces. Abstractions should not depend on details. Details, concrete implementations, should depend on abstractions. I think for this principle, it's a little clearer in pictures than in words. And as alluded to previously, adhering to this principle makes it easier, among other things, to create mocks. Okay, additional considerations. When designing the API shouldn't have features that exist only for testing. API choices shouldn't prevent testing. And we may need a way to stub out system dependencies. And keeping all of that in mind, I will hand it over to John.
Thank you.
Thank you, Aram. I'd now like to discuss several techniques or practical recommendations about how to apply the solid design principles to make your code more easily tested or testable, both for yourself and for the people using your libraries. We're going to start with the pointer to an implementation idiom or pimple, which makes it dramatically easier for you, in many cases, to test your functionality. Then we'll move on to using the combination of the polymorphic open-close principle, the list-cuff substitution principle, and the dependency inversion principle to make the recommendation that anything that may need to be mocked out for testing purposes should be provided only as an interface or passively a functor. Then we'll move on to something that I personally find a little bit more exciting, which is the idea that we can use something along the lines of resource acquisition is initialization style guard, kind of think a lock guard, in order to install and extend test-only APIs for an object. And we'll have a nice example for that, I believe. And then I'll finish up with abstract factory methods and how they have some specific applications towards testing. In all of these cases, I'm going to be taking examples from the open source libraries that Bloomberg has published, in particular BDE, which is our version of the standard library, plus a whole bunch of utility classes, plus a couple layers of abstraction, or BlazingMQ, which is a message queue system that we open sourced maybe last year. I don't see Taylor, he'd know. And is a very nice message queue system if you need to support fan-out functionality, or if you need to acknowledge messages out of order. I think it may be the only one that allows you to acknowledge messages out of order. So just in case anyone isn't familiar with the pimple idiom, it's basically what it says on the tin. You have a pointer to an implementation. The basic idea is that if you have a public API, but you have different implementations that depend on different environmental factors or other things where they may want to be different, like say for testing, then you are able to isolate those different isolations into the specific implementations. Here we have a foo class implemented without pimple and then with pimple. So the version on the left does not have it. It is simply a class that has some number of internal data structures and functions associated with it. If you had things that depended on your runtime environment or the hardware or whatever else, then in order to test those, you would need to set up whatever those requirements were in order to select that particular portion of the code. And if you're talking about something where it's hardware support versus not hardware support, this means you may need different test environments in order to meet those requirements. Where the version on the right, which has the implementation separate from the actual class, and you can see that it stores that implementation, in this case using a unique pointer. During construction, it can figure out which version of the implementation that it needs, and then the APIs that you call through the public API, it just goes to whatever the current underlying implementation actually is. So if we look at BlazingMQ's CRC32 checksums, the public API has a calculate class that takes some data and a length of that data, and it returns the CRC32 checksum. But the implementation has two versions, one of which is calculate software, which is CPU based, and the other one which is calculate hardware serial, which is hardware based. And so if we're in from a testing perspective, having these separate implementations means that you could have a single environment that supports the hardware acceleration and still do both sets of tests on that environment. Therefore making it a bit easier for the library implementer to actually make the tests. So next, I'd like to suggest that via as I think we've said 3 times now, the polymorphic open-close principle, list cup substitution, and dependency inversion principles, basically combine to say that we really should depend only on interfaces if it's something that someone will need to make a mock of or make an alternate version of for testing purposes, or possibly other uses. And this also, we should also call out that you may also need to mock out things that are not class-based, like say a system call. So the way that we wrote this is object-oriented, but of course this does not have to be object-oriented. You could pass the dependent interfaces as arguments to the functions as well, if you are a functional programmer. But if you're doing this object-oriented, you can pass the interfaces into the constructor and then store them for later use, of course being careful about your lifetimes. This means that for testing purposes, if say you have something that is implemented on top of an I/O layer, you could do things like pass in a mock version of that I/O, of that TCP connection or something, and then you could check your error handling and see whether or not it's correct for it timed out, the connection failed, or some sort of other ambiguous error, where actually doing those tests in real life would be time-consuming or difficult, specifically trying to get the individual conditions that would cause that test to fail, the underlying implementation to fail in a specific way. Of course, you may depend on something that isn't an interface. In this case, an easy solution is to pass in a functor. Again, if you're a functional programmer, you don't have to put this in the constructor. You could pass this in as an argument to the functions that need it. And so you could wrap up, say, a call to read in a functor and pass it in so that you could have a read that failed consistently in interesting ways. The big caveat here is that if you do this, you really want to make sure that the default is the production behavior. Because if you don't do that, you've just made an API that is exceptionally easy to misuse. And of course, one of the goals with API design is keeping things easy to use and hard to misuse. I would also suggest that you probably want to pay it forward in terms of people that are trying to use your library to build their library. And that is that you may want to go ahead and provide interfaces on top of the classes that you're implementing. Again, this is just making it easier for the next person in the chain of libraries. And you may be in a situation where, for various reasons, like say you're really trying to avoid heap allocations, or you really care about that one clock cycle lookup for the vtable, you can also do this with templates. In this case, the template argument is the thing that you depend on, and you can either take it in the constructor and store it for later use, or pass it in as part of your function. And then the real version of it would be a foo that depends on a real bar, and the test foo would be a foo that depends on the test bar. And depending on the circumstances and whether or not you want to force the person in one layer up to also do this again, you can also go ahead and provide an interface or not. And as an example, particularly in the BTE code, which has had allocators for a while now, or more recent versions of C++, which are written to be allocator aware, the allocator is actually a pretty nice use case of things that can be swapped out. And while it's not strictly a interface in that it is a real thing, but it does have virtual functions, the various allocator implementations can actually be really handy. From a testing perspective, a test allocator which easily detects memory leakage for the object under test is really, really nice. And also a local sequential allocator can situationally give you real performance boosts in production code. Now I'd like to move on to the thing that I find exciting, which is, well, I use a lot, which is to basically use the single responsibility and interface segregation principles, which tell us we should not have test-only APIs on our public API, and therefore, how do you extend it? So we're actually going to cover 2 ways to do this. One of these is to use guard in the style of lock guard to modify the innards of the production class and to provide additional APIs. My favorite example of this is from BDE, and it's the event scheduler. And the event scheduler lets you pass in functors and tell it when to execute them. And it will do its best to execute them at that time. But one of the things that's coupled with it is the event scheduler test time source, which the way that you apply it is you have to instantiate the event scheduler, you instantiate the test time source, and you pass it the scheduler as an argument. After that, you're free to use the scheduler as normal, but rather than waiting for whatever amount of time you're supposed to wait, you can instead just call advanced time on the test time source, and the event scheduler will act as if that amount of time has passed. This makes it much, much faster to run the unit tests that rely on an event scheduler than it would be without the test time guard, or the test time source. So the way that you would go about implementing this in a super generic way is that you would need to have an object which is, so you have a foo, and there's something in foo that would need to be modified, probably foo data or something like that, in order to implement the test behaviors. And the class foo would need to befriend the test guard. And then when you were going to apply the test guard, you pass it in as part of the constructor. The test guard would then modify the foo data as needed, and then provide the test APIs in addition. It's not quite as bad as it sounds. But this is one of the things that you can do to make it much easier for the people that are using your libraries, while still keeping your APIs under control. There is a small caveat with it, in that if you end up having a class that completely owns a foo, then there's no way to install the test guard and testing environment. Of course, you'd have to go through some hoops in order to actually have actually get at the foo anyway. And so instead, if you use this pattern, then you are forcing people to have classes that use a foo which get passed in or attached to the end of your functions. And this allows the test guard to be installed before the foo is installed. The last thing I would like to talk about before passing the microphone to Lukas is the use of the abstract factory pattern for testing purposes. The abstract factory pattern is, of course, the way that you collect a tightly coupled set of interfaces and therefore have the ability to swap them out somewhat more easily. And the version of the Gang of Four book that I have, it's on page 87, and they are specifically talking about swapping out the UI components for Motif for other graphics libraries or widget libraries. I do hope that whatever that project was has been updated to at least use less teeth. I guess, yeah. Anyway, sorry. Of course, one of the other things that the factories can do is they can actually provide additional test APIs in a similar way that the test guard did for the components for the test components that they're providing. So of course, the way that you would just do this is if you have a factory interface that your class is dependent upon, the production version would use a real factory, and the test version would use the test factory. And this is handy because the only time that the decision about which types you're using is made is when the concrete version of the factory is instantiated, making it easy to switch. For my example in this one, I would like to point at the channel factory from LazyMQ. I know that the API looks a little bit unusual, but what's actually going on here is that the handle, which is populated as a second argument in listen, is the object that's being produced, and the thing that can be used later to perform various types of I/O. But if you actually look at the test channel factory implementation, it provides a wide variety of additional test-specific functionality that you can use to directly modify what's going on for anything that's trying to use that handle. And with that, I would like to now turn it over to Lukas in order to talk about how to apply these principles more generally. And yeah.
Thank you, John. Next, we will talk about, we'll take a look at the different techniques of generalized marking and testing. We'll also discuss a few challenges of using these techniques. And in the end, we will propose a tool that aims to solve these problems and improve life quality. Okay, as mentioned earlier, marking with dependency injection can be done by using an abstract interface or using a template type. And also, we want to ask the question, who is actually responsible for dependency injection? So here is an example of using an abstract interface. Here we have a pure virtual interface class .i here, and it has a pure virtual function bark. So this interface class is the abstraction that the other components want to depend on per the principle of depending on abstraction, not the concrete implementation. So the concrete implementation class dog is derived from the interface class .i, and it overrides the bark function, implementing what the bark function actually does in the production code. So we also have a mock here, dog mock. It is also derived from the interface .i, and it overrides the bark function with a mock function. And here in this example, the mock function is implemented using Google Mock. So when another component here, my business, want to depend on the dog, you can hold a pointer pointing to a pointer of the interface type .i, and in the constructor, you can open up for dependency injection. So in its function, do something, it can perform its logic by invoking the bark function through the interface type pointer .i here. In the case of production code, we're going to inject a real dog when we construct my business. So the real bark function gets called when the do something function gets called. And in the case of unit test, we're going to inject a dog mock here. So the mock function gets called when we test the logic of do something. So that's simple. This is how it usually looks like in the unit test code. In the text and fixture, we can declare all the dependency mocks first, then we'll declare our subject under test, SUT. Then at the setup portion, we will first instantiate all the dependency mocks, then we'll instantiate the SUT. And this is where we inject all the dependency mocks into the SUT. So to test the logic of my business do something function, here we say, when this function gets called, we can expect our mock function gets called. And we can expect the mock function gets called in a very specific way that we want. For example, we can verify how many times it gets called, what arguments are passed to our mock function. We can also tell the mock function what to do when it gets called, like return a certain value. Or if some arguments are pointer types or reference type, we can even set the storage value to these arguments. So mocks are very flexible, easy to use, and we have full control over them in our unit test. So here is an example of using the template type for dependency injection. As we mentioned earlier, we generally don't recommend this approach unless you really cannot have dynamic memory allocation, or saving one CPU cycle is really your goal. Now we want to ask the question, who is responsible for dependency injection and how? In this example, we have a class awesomlib here. It derives from its interface awesomlib.i, and it opens up for dependency injection here with the argument ABC service interfaces, right? Now we give this class to our user. Then our user will be faced with the question. They will be required to inject dependencies at some point. So this is something we don't want to do. we don't want to burden our user with injecting these dependencies that are actually our internal implementation details. So what should we do here? So one approach, again, is use pinball idiom. So here we have this awesome lib derived from the interface. And inside this awesome lib, it holds a pointer pointing to another class, awesome lib implementation. So in the awesome lib imp is actually our concrete business logic implementation, and it opens up for dependency injection. Instead, in awesome lib, what we'll do is its constructor will construct all the real dependencies as a real concrete implementation, like a ABC service here, and it will inject them into the awesome lib imp. And all the public member function will just simply forward the call to the awesome lib. So in this way, when we give the user the interface, the mock, and the class itself, the user will not be required to do any dependency injection that they don't care about. And benefit for us, we can still fully test our business logic by unit test awesome lib imp, because there we can actually inject the mock services as dependency into the SUT. So the code looks something like this. So on the left, we have the awesome lib derived from its interface, holds a pointer points to the awesome lib imp, and in its constructor, here we instantiate all the dependency ABC services, and then we inject them into the awesome lib imp pointer when we instantiate the imp pointer. Then it will just simply forward all the calls to the awesome lib imp. And awesome lib imp on the right implements all the real business logic, opens up for dependency injection, and it can be fully unit tested where we inject the mocks in our SUT. Another technique is usually called performance dependency injection. Here we have two overloaded constructors here. One constructor doesn't expose all the internal dependency to the user. Instead, it will just construct them with a real implementation. And this copy of constructor is probably likely the one we want to give to the user, so they can call this one when they use our awesome lib class. The other constructor will be the normal one, opens up for dependency injection, so we likely will use this one in our unit test, where we can inject the mocks to fully test our code here. So now we want to talk about some challenges. So from what we showed earlier, just a few slides, right, we can immediately see that the upfront of investment is unpleasant if we want to write properly testable code, right? So even if we successfully convinced like new CPP programmers that the investment is worth it, because typing on the keyboard is never the bottleneck of your software cycle. It is when the bug escapes to production environment, it comes back to bite you, and you have to debug and fix them. That's where the real pain is. So they understand that, but then they're faced with another challenge. They may not be familiar with all these new patterns and various techniques, and they don't know where to start with. When you think about it, often the change is fairly small in the daily, sometimes, right? So it seems like they can just add a few lines, make it work, not caring about testability or design principles. So always seems like it is easier not to do the right thing. So we face this problem a lot when we teach the new CPP programmers, and we think about this a lot. So we think we should have a good solution. Maybe we can come up with a tool that will make actually do the right thing easier, and something like a one-click design pattern generator. So this tool can be like a script that will ask you a few questions, understands what you need, and create all the boilerplate code for you. So the interfaces, the mocks, the unit test, pinball idiom, if you wish to, et cetera, et cetera. And the generated code would be able to compile out of the box with the specified patterns already in place. Such a tool doesn't only help you code faster, but should also help you code better by following solid design principle out of the box. not needing to write boilerplate code by hand means that encouraging you to write small classes following the separation of constraint principle. You don't need to set up unit test because they're already set up for you out of the box. So you can just focus on implementing the test and implementing the functionality together. It creates the interface, mocks, pinpoint EDN on demand, can generate useful hints, and the code it generates should have high quality. That's an example for modern C++. So that's some of our thoughts. With that, this is the end of our talk, and we're happy to answer any questions. Yes.
So the tool proposal, is that like a proposal for people to do that, or have you written one yourself?
All we can say right now is that keep an eye, watch on the Bloomberg GitHub. And if we have an update, we should have an update soon and for that to come. But we cannot talk more right now, unfortunately.
So if you were to suggest us proposing a tool that we use, some hypothetical tool, would it be based upon like when you said user input from the user, some configuration file thing, or would it actually take the code and use it like with something like libplain and be able to generate stuff from that itself? I
think the implementation details can be a lot. There should be a lot of ideas how to implement this. Here we're only saying the specification, what our tool should do. But anyone is free to come up with their own ideas. I'm sorry, I cannot go into more details about that.
So in a lot of the slides, there was an implementation class which is used by default in production. Is that implementation class part of the public interface, just please don't use? Or is that hidden away somewhere outside of the public API?
Well, if it's called input, it should be please don't use, and we have ways to put them to the private part of the library. So there is ways to deal with them. We should provide the public interface for people to use.
If they are hidden away, how do tests have access to those dependency injection interfaces?
Oh, that's for our own, right? That's for our own tests.
Right. How do the tests have access to that?
CPP file for test.
When you're using the pointer to implementation, that's helping the library author write tests. It's not necessarily helping the people using the library to write tests. The dependency injection mechanism and the mechanisms that were proposed to extend the APIs for testability are the methods that are applicable for the library user as opposed to the library author. So the pointer, the simple idiom hiding the implementation details is something that helps the author, not the user.
So you guys mentioned using mocks a lot in the presentation. How do you choose when you're going to use a mocking framework versus using a different type of test double?
So in my personal opinion, mocks is usually better than the double or stub or fake, right? So I'm sure a lot of people agree with that. But regarding choosing different framework, here we're only trying to say the principle here. You're free to choose other different mocking testing frameworks, such as the newer ones. I forgot what's the name called.
I have a slightly different answer. 3 people would probably have 4 opinions. I think it really depends on what you're trying to test. So if you're trying to test the error behaviors of, say, something that's using a library, then very often you have to use kind of a homespun replacement in order to be able to force the appropriate error returns. So if you had a function that normally would do something and return success and an error, you have a very simple substitute, which probably doesn't meet quite the standard of a mock, but you could just say, okay, in this case, I'm going to replace my IO function with one that returns could not connect or something like that, or read error or something. And that way you can directly test the error handling is correct. That would be a situation where you wouldn't want just a mock from
You mentioned at the beginning that system tests generally don't test the unhappy part. We do that at integration test and unit test level. But I'm wondering if you've got views on mocking low level, like I would say this system call returns, times out, or some system call returns at the intra. Sometimes will affect, like only at the system level, kind of the test will pass at the unit test level. Do you have experience of doing that? And does this approach work well there? Was it only for the unit test?
So the reason why you don't usually test for that stuff at the system test level, or sometimes even at the integration test level, is the setup for that can be hard. If you had a way to consistently set things up at that level, then it's completely reasonable to test for it there. And especially if you're moving from legacy, if you're on a legacy code base, like some of this might be, very often you have to test at the integration test or even the system test level for a lot of those unhappy path behaviors. There are, I don't remember whether or not it's publicly available, there are libraries that will do things like induce horrible TCP problems for you, so you can see how those horrible TCP problems affect things that are running in production, or running in a production-like environment. And then you could consistently see whether or not your systems can survive that. And of course, you could do chaos testing and things like that. But the general reason why this talk especially was focused at the lower level of tests, and at the beginning we said it was hard and time-consuming to do that, is that the setup is hard. Not that there isn't value in doing that, it's just usually unreasonably time-consuming to do that. But you may only have that choice. If you have 10,000 lines of code that you need to refactor, you may need to start by writing a very high-level test that verifies the issues.
I guess related is like how far up that pyramid your unit tests go. Like you just do it like the kind of very leaf node classes and functions, or you unit test bigger chunks.
So you can certainly use a unit test framework to write integration tests. I think a lot of people, when they're first coming into the testing world, will accidentally write a significant number of integration tests that they think are unit tests, which usually need to be fixed later. But that was kind of the reason why we were trying to, we circled both of them and tried to define what they were more or less by functionality rather than by what framework you were using.
We have time for one more question. Okay.
So there's kind of like a chicken egg type thing in these regards. So what's your thoughts on the design of your system dictating how you test versus how you test dictating the design of your system?
Okay. So as we said, the design of your system has very deep synergy with the testability of the code. So usually tests are very good feedback for a design decision. At some point, well, you can go ahead. There are many ways, right? Like the TDD TDD practice would first write the test, then you would go around to implement the red, the green, then change the test, red, green, right? So that is very much the tests are dictating how the design can go, right? So you can also go the other way. You first have your design, then you start to write the test. But at some point, maybe you're like, I have a very problem I cannot test here. Then this is when the test is giving you a hint that you probably have somewhere the design has a opportunity to refactor, make it better, right? Make it even loosely coupled components between each other, and then your code will become testable again. So does that answer your question? Hi, Sherry.
Is there a connection between the simplicity of the design and the ability to test? I mean, does it sort of Does it, if you create a very straightforward, simple, one step after another design, and it's easy to test, does that ultimately lead you to have better code?
Yes. I'm sorry, it's both. Yes, absolutely. Okay, I think that's the end of the talk. Thank you, everyone.